Hello, and welcome to this in-depth presentation on forward kinematics and inverse kinematics. In the next several minutes, you will learn how to calculate the position and orientation of a robot's end effector based on joint parameters, and conversely how to determine the joint parameters needed to reach a desired position and orientation. Let us begin. Today we explore two complementary problems in robotics. The first is called forward kinematics. In forward kinematics, we start with the values that describe each joint of a robot, for example the angles of rotational joints or the extension distances of sliding joints. Using those values, we compute the exact position and orientation of the robot's tool or end effector in three-dimensional space. This process is straightforward and involves multiplying a series of transformation matrices. The second problem is inverse kinematics. In inverse kinematics, we start with the target position and orientation that we want the end effector to achieve. From that target, we must solve for the joint values that will place the tool in exactly that pose. Inverse kinematics is more challenging because there may be more than one valid joint solution for the same target, or in some cases no valid solution at all when the target lies outside of the robot's reachable workspace or in a singular configuration. Before we dive into the calculations, we need a consistent way to describe the geometry of a robot. We represent a robot as a chain of rigid links connected by joints. Each joint is either revolute, meaning it rotates, or prismatic, meaning it slides. To describe how each link is positioned relative to the previous one, we attach coordinate frames to each link and use what is known as the de Navit-Hardenberg convention. Under this convention, each connection between two links is defined by four parameters. The first parameter is the link length, which is the distance measured along the previous frame's x-axis between the two joint axes. The second parameter is the link twist, which is the angle between the two joint axes measured around that same x-axis. The third parameter is the joint offset, which is the distance measured along the new joint's z-axis between the two link frames. The fourth parameter is the joint angle, which is the rotation around that same z-axis. For a revolute joint, the joint angle is the variable and the joint offset is fixed. For a prismatic joint, the joint offset is the variable and the joint angle is fixed. Once we define these four parameters for each link, we can build a 4x4 matrix called a homogeneous transformation matrix. Each of these matrices expresses the position and orientation of one link frame relative to the previous link frame. To perform forward kinematics, we take the transformation matrix for link 1 relative to the base, multiply it by the transformation matrix for link 2 relative to link 1, multiply that by the transformation matrix for link 3 relative to link 2, and so on until we reach the end effector. The result of this multiplication is a single 4x4 matrix. The upper left 3x3 portion of that matrix encodes the orientation of the end effector, and the upper right 3x1 portion encodes the position of the end effector in the base frame. Let me illustrate this with a simple example of a 3-link planar robot arm. Imagine 3 straight segments connected by rotating joints. All 3 joints rotate around an axis perpendicular to the plane of the arm. We label the lengths of the segments L1, L2, and L3, and the joint angles θ1, θ2, and θ3. In this special case, the orientation parameter that twists one link relative to the next is always 0, and the joint offsets are 0, so the mathematics simplifies. The position of the end effector in the plane can be written in words as follows. The x-coordinate of the end effector equals the length of the first link times the cosine of θ1, plus the length of the second link times the cosine of the sum of θ1 and θ2, plus the length of the third link times the cosine of the sum of θ1 plus θ2 plus θ3. Likewise, the y-coordinate of the end effector equals the length of the first link times the sine of θ1, plus the length of the second link times the sine of the sum of θ1 and θ2, plus the length of the third link times the sine of the sum of theta 1 plus theta 2 plus theta 3. If you plug in any three joint angles, you immediately compute the two-dimensional position of the tool. This direct calculation is fast, exact, and suitable for real-time control and animation. Forward kinematics is used in many applications. In a control loop, encoder sensors measure the actual joint angles, and forward kinematics converts those angles into the real-world position of the tool. In simulation or visualization software, forward kinematics animates the robot moving through a sequence of joint angles. In collision detection, forward kinematics computes the space occupied by each link so the system can check for obstacles. Now, let us turn to the inverse kinematics problem. Inverse kinematics asks the question, given a desired position and orientation of the end effector, what joint angles or displacements should we use to achieve that pose formally? We start with a target homogeneous transformation matrix that represents the goal orientation and goal position in the base frame. We then solve a system of nonlinear trigonometric equations to find the joint variables that reproduce that matrix when plugged into the forward kinematics multiplication. Inverse kinematics is more difficult because there are three main challenges. First, there may be multiple solutions. A two-link planar arm, for example, can approach the same point with its elbow up or its elbow down. Second, there may be no valid solutions if the target lies beyond the robot's maximum reach or if the goal orientation cannot be matched. Third, the equations are nonlinear, involving sine and cosine functions of sums of angles, and cannot generally be solved by simple algebraic manipulation except in very special cases. For certain simple robot geometries, we can derive closed-form solutions. Returning to our planar two-link arm example, imagine two straight segments of length L1 and L2 connected by two rotating joints. The first joint is at the base and the second joint attaches the second segment to the first. The end effector is at the tip of the second segment. Suppose we want the end effector to reach a point with coordinates x and y. We first compute the straight line distance from the base to the target point, call that distance r, equal to the square root of the sum of x squared and y squared. Next, we apply the law of cosines to the triangle formed by the two links and the line from the base to the target. That gives a value for the cosine of the second joint angle equal to the quantity r squared minus L1 squared minus L2 squared, all divided by 2 times L1 times L2. Taking the arc cosine of that quantity gives us the magnitude of the second joint angle, and there are two possible signs for the square root that correspond to the elbow up or elbow down configurations. Once we choose one of those two solutions for the second joint angle, we compute the first joint angle by taking the arctangent of y over x, then subtracting from that the arctangent of L2 times the sine of the second angle over L1 plus L2 times the cosine of the second angle. This formula yields one valid pair of joint angles. Choosing the opposite sign in the square root yields the second valid pair. When robots have many joints or more complicated shapes, closed-form solutions may not exist or may be very cumbersome to derive. In those situations, we turn to numerical methods. The most common numerical approach uses the Jacobian matrix, which expresses the relationship between small changes in joint variables and small changes in the end effector's position and orientation. Specifically, if we denote the vector of joint rates by dot theta and the spatial velocity of the end effector by a 6-element vector containing linear velocities and angular velocities, then the Jacobian matrix times dot theta equals that spatial velocity. To solve inverse kinematics, we compute the difference between the current end effector pose and the desired pose, which we call the pose error. We then multiply the pseudo-inverse of the Jacobian by that pose error to obtain a set of joint velocity commands. By integrating those commands over time, the joint angles converge gradually to a configuration that reduces the pose error to 0 or near 0. Another approach is to formulate inverse kinematics as an optimization problem. We define a cost function equal to the squared distance between the current tool position and the desired tool position, plus a regularization term equal to a penalty weight times the squared distance between the joint angles in a preferred reference posture. We then use standard nonlinear optimization solvers, such as Levenberg-Marquardt or sequential quadratic programming, to find the joint angles that minimize that cost subject to constraints such as joint limits and collision avoidance. Inverse kinematics also faces practical challenges. One major issue is singularities. A singularity is a robot configuration where the Jacobian matrix loses rank, meaning that certain end effector motions require infinite joint velocities. To handle singularities, we often use a damped least squares approach, which adds a small damping term to the denominator when computing the pseudo-inverse. This stabilizes the solution and prevents joint rates from becoming unbounded. Another issue is redundancy, which occurs when a robot has more joints than strictly necessary to reach any given pose. Redundancy can be an advantage, as it allows us to optimize secondary objectives such as avoiding obstacles, minimizing energy use, or staying away from joint limits. We project those secondary objectives into the null space of the Jacobian so they do not interfere with the primary task of achieving the desired end effector pose. Finally, physical joint limits must be respected. We handle those either by clamping joint values within allowable ranges or by adding penalty terms to the cost function that discourage violation of the limits. Forward kinematics and inverse kinematics are essential in a wide variety of fields. In industrial automation, robotic arms use inverse kinematics to position welding torches, grippers, or cutting tools with millimeter accuracy. In computer graphics and animation, artist tools use inverse kinematics to pose character limbs automatically, sparing animators from keyframing each joint individually. In virtual reality and motion capture, motion data captured from a human actor is mapped to a digital avatar through inverse kinematics, ensuring natural movement that respects the avatar's joint constraints. In medical robotics, surgical manipulators use precise kinematics to guide instruments along planned trajectories inside the human body, greatly improving safety and accuracy during minimally invasive procedures. To summarize, forward kinematics is the direct calculation of an end effector's position and orientation from known joint parameters by chaining homogeneous transformations. It is fast, exact, and linear once the transformation matrices are defined. Inverse kinematics is the inverse problem of finding joint parameters when given a desired end effector pose. It is generally nonlinear, may have multiple valid solutions or none at all, and typically requires either closed-form derivations for simple robots or numerical and optimization methods for more complex robots. Key challenges include handling multiple solutions, avoiding singularities, exploiting redundancy, and respecting joint limits. Thank you for listening to this detailed presentation on forward kinematics and inverse kinematics. I hope this script gives you both the conceptual foundations and the practical tools to implement these algorithms in your own robotics or animation projects. Good luck, and enjoy applying kinematics.